In this lecture, we shall consider solving a cantilever beam with a combination of various loads for shear force and bending moment set up in a section along its length. Let's have a cantilever beam AB of length 5 meters with end A fixed and end B free. Let's show a point load of 10 kilonewtons acting at the free end B. A uniformly distributed load of 20 kilonewtons per meter is shown acting over a length of 1 meter at a distance of 1 meter from the free end. Important key points are marked over the beam and labeled accordingly. Let's have a counterclockwise moment of value 30 kN meter acting on the beam at point D. Let's also show a triangular uniformly varying load of value 0 kN per meter at point C and increasing uniformly over a length of 1 meter to attain a maximum of 25 kN per meter over fixed end A. We mark the relative lengths of each part of the beam from the adjacent ones. Let's consider free end B as reference and mark an arrow pointing towards the left, labeling it as X, indicating the distance of the imaginary section from this reference end. Now we drop down the projections from the various key points and draw the zero datum lines for shear force and bending moment diagrams. Let's begin the calculations by writing the shear force equations for various parts of the beam separated by the key points. For span BF, for which X ranges from and including values 0 and 1 meter, shear force at X equals plus 10 kilonewtons, which is a constant. For span FE with X varying from 1 to 2 meters, the shear force at X equals plus 10 plus 20 times X minus 1 kilonewton, which is found to be linearly varying over this span. For span ED, X varies from 2 to 3 meters, for which the shear force at X equals plus 10 plus an equivalent point load of 20 times 1, which gives 30 kilonewtons and is a constant. For span DC with X varying from 3 to 4 meters, shear force at X is again written as plus 10 plus 20 times 1, giving 30 kilonewtons as a constant value, since the applied moment of 30 kilonewton meter at D does not affect the value of shear force at the location. Finally, for span CA, where X changes from 4 to 5 meters, we first find the unknown ordinate of uniformly varying load represented by question mark symbol, for which we use the concept of similar triangles as discussed in earlier lectures. Without going into the labeling details, we directly write the relation to find the question mark as question mark over x minus 4 equals 25 over 1. Hence the ordinate equals 25 times x minus 4 kilonewton per meter. The shear force at X equation for this span CA can now be represented as plus 10 plus 20 times 1 plus an equivalent point load acting at the center of the triangular area, that is half times x minus 4 times 25 times x minus 4, and this gives plus 30 plus 12.5 times x minus 4 to the power of 2, which is parabolic. Examining the double derivative of the shear force at X equation with respect to X, we find that it is positive in sign, meaning that the parabolic curve obtained is of a minima type. Now, we proceed with writing the equations for bending moment at X for various spans of the beam. For span BF, M at X equals minus 10 times X, which is a linear variation over X. For span FE, M at X equals minus 10 times X minus 20 times X minus 1 times X minus 1 over 2, which gives minus 10 times X minus 10 times X minus 1 to the power of 2, which is parabolic. The double derivative of M at X equation gives us a negative sign, indicating that the curve is of a maxima type. For span ED, M at X equals minus 10 times X minus 20 times 1 times X minus 1.5, which is found to be a linear variation over this span. For span DC, M at X equals minus 10 times X minus 20 times 1 times X minus 1.5 plus 30 kilonewton meter at D for creating sagging bending moment at the section. This equation also is linear over the span DC. Finally, for span CA, M at X can be written as minus 10 times X minus 20 times 1 times X minus 1.5 plus 30 minus 12.5 times X minus 4 squared times X minus 4 over 3. Here, we consider the equivalent point load value found in the shear force equation for span CA, which is 12.5 times x minus 4 squared, to help us in writing the corresponding bending moment equation directly. This equation is found to be cubic with respect to x. The double derivative of the bending moment equation gives us the negative sign. Hence, the variation curve is found to be of a maxima type. We now finally proceed with showing the values of the ordinates for shear force and bending moment over various key points and connecting them by the locus curves as found from the corresponding equations for various spans of the cantilever beam. We label the same accordingly for quick reference. The maximum shear force and bending moment values are found to occur at the fixed end A of the cantilever beam, with values of 42.5 kilonewtons for shear force and 94.17 kilonewton meter for the bending moment. In the next lecture, we proceed with solving one more problem of a cantilever beam with a combination of loadings over its length.